Hello, everyone. My name is Nicholas Clark, and I study boundary layer meteorology here at Texas Tech University. And today I'm going to be talking about the complexities and boundary layer dynamics over mountainous regions and how these dynamics affect the vertical distribution of trace gases. Okay, so I'm going to begin with a brief introduction of some of the terminologies that will be important to understand for this project. And then I will move into the data sets that we used and how it was formed. Then I'll move into the methodology that we use to understand these dynamics, which will lead us into the research questions we hope to answer. And last but not least, we'll talk about some of the importance of this work. And then we'll conclude it from there. Okay, so what is the atmospheric boundary layer? The boundary layer is the lowest 2 to 3 kilometers of the Earth's atmosphere that is directly affected by the Earth's surface forcing, which include things like friction and the heat transfer between the Earth and the atmosphere. Okay, so an important characteristic of the boundary layer is that it's not static. It relies on incoming solar radiation to grow in depth. Okay, so as a result of this, we typically see deeper boundary layer depths in the afternoon as opposed to the morning, which creates its diurnal cycle or its daily cycle. Now, this growing and shrinking in height is actually a type of exchange process between what lies above the boundary layer, which is called the free atmosphere or the free troposphere. And as a result of this growing, we can see how it might push up constituents within the boundary layer into the free atmosphere. Now, vice versa, the free atmosphere can push things back into the boundary layer through a process called entrainment. So we have sort of a into the boundary layer and an out into the boundary layer, which creates a sort of flux or a budget or a net. And this net is actually often viewed as the concentrations of various gases in the free atmosphere. Okay, so an important, there's many different phases of the boundary layer cycle. The one we'll be looking at primarily for this one is actually this mixed layer, where we see, this mixed layer means exactly what it is. Basically, all the air within this layer here is well mixed. And as a result, trace gases that we might find near the bottom of this boundary layer are roughly equivalent to the trace gases above here. The concentrations are roughly the same. Now, this changes based on different phases, but this is basically how it works in the mixed phase or the convective boundary layer. Now, this leads us into the orography of it all, or the mountain part of it all. So as a result of an inclined terrain, we actually have a change in the amount of solar radiation and heat transfer between the Earth and the atmosphere. Now, as a result of this change, we see a change in boundary layer features. During the morning over complex terrain or over mountains, we see a very shallow boundary layer that actually follows the terrain. You can see this here in this image here. You'll see how we have sort of this grayer area is very shallow, close to the terrain. And then as we go into the valley, it deepens. But then as we go back up, it's once again very shallow. Now this compares to the valley over here as well as being very shallow. However, as the day progresses and we begin to see more and more incoming solar radiation, this terrain dependency actually begins to sort of die down, and we begin to see a boundary there that is once again flat and independent of its terrain. So that's one thing that we're interested in looking at. Another thing is the many complex regional flows within the mountainous regions as a result of uneven surface heating due to uneven terrain. And there are many different airflows that go in within the mountains. For instance, I've listed a few here: the upslope, downslope winds, the valley to mountain winds, and there's many others. They are on various scales, so it can be very complicated. And lastly, as a result of all this, we actually see an enhanced amounts of vertical mixing in the mountains. So we can expect to see trace gases that are actually similar with respect to height. Okay. So I've been mentioning trace gases throughout this, but what exactly are there? Well, they are the gases that make up less than 1% of our atmosphere. And just because they make up very little doesn't mean they don't have a large impact. In fact, many of them are directly related to things like climate change, and we'll see how that is here in a second. So the first thing we'll be looking at, the first trace gas or tracer, is water vapor. Now, water vapor is essential to understanding weather phenomenon because they form clouds, and eventually then that forms precipitation, which is all a function of water vapor. Also, water vapor is a greenhouse gas, so it contributes to the warming of our atmosphere and the resulting looming crisis of climate change. And then that leads us into the next one, carbon monoxide, which is actually doesn't directly impact the atmosphere in many ways. However, it does react with certain elements that would otherwise react with other things that can directly affect the atmosphere. For instance, it can oxidize into carbon dioxide and ozone, which are carbon dioxide is a greenhouse gas, and tropospheric ozone is actually very dangerous. And it also can react with hydroxyl radicals that would otherwise destroy methane. And I will go ahead and talk about methane now. And methane is our third gas, and it is also a greenhouse gas. In fact, it is amongst the strongest. It is 84 times more heat per mass than carbon dioxide. However, it does exhibit lesser concentrations. But yeah, these are the trace gases we'll be looking at. So we'll need to understand them a little bit. The data set we used for this project is called ACT America. And ACT America is a series of aircraft measurements campaigns over 3 regions of the United States. Now, for this the purpose of this project will be actually only looking at one of these regions because it is the only region that actually contains the presence of a mountain, the Appalachian Mountains, and that is in the Mid-Atlantic region. There are 2 other regions, the Southern region and the Midwestern region, which take place over more or less flat terrain. Now, it actually took place over 4 years, 2016, 17, 18, and 19 in 5 different seasons. So there were 2 seasons in one of the years where they took measurements. And for each flight campaign, well, given that there were no issues with the flight or the aircrafts and on that particular day, they used 2 aircrafts. One is a B-200 and the other is a C-130. And now they are equipped with their own particular instrumentations. And two of the main ones that we'll want to be looking at is the cavity ring down spectroscopy system, which is a Picaro instrument, which is how I will refer to it as. And also we have a cloud physics LiDAR, or a CPL, which can measure a vertical line in the atmosphere, and we'll see some images from it. I will be able to explain it better, but that is actually on board the C-130 only. So they're both equipped with the Picaro instrument. The C-130 has a cloud physics LiDAR, or a CPL. Okay, so the idea behind all of this is that as the aircrafts during the measurement times, during the dates that they took measurements, the aircrafts are flying over the Appalachian Mountains. And as a result, they got to fly up and down to avoid mountains and to, just to fly under safe conditions in general. And as a result of that, we see points where the aircraft is within the boundary layer, and sometimes it's above the boundary layer. Now that gives us an opportunity to look at how the concentration between these two vary over complex regions. And so how do we do that? Well, first we have to find suitable flights that actually exhibit this behavior. They don't all do it, but once we do that, we're hoping to get out to maybe 10, 12. That's kind of our aim. So in all the seasons that they've measured, which should hopefully be every season. But yeah, we look for particular aircrafts, tracks that exhibit this behavior. I have an example here, 2016-07-25. If you look at this top image here, with the red line. This red line here is actually the flight track of the B200. So you can see how it kind of goes up and down and then back up and down. And then this blue line is actually the terrain below. Okay, so first off, if we're going to understand how the exchange processes work between the free atmosphere or the free troposphere and the boundary layer work, we have to identify points in which it actually crosses from one to the other. And the way we do this is through the use of its potential temperature. Now, potential temperature is just the temperature a parcel of air would need to attain if it were adiabatically brought down to sea level pressure. Now, that's a lot of words, so but it's a very, it is useful to understanding where at points we might look for the boundary layer depth, which is essentially what we're looking for when we're trying to find the point at which the aircraft moves from the boundary layer into the free troposphere. And so we have to look at this potential temperature with respect to time, because typically at the boundary layer, we're going to see an increase in potential temperature due to an inversion. So we're going to see a jump in potential temperature. So we need to look for jumps in potential temperature. And the way we do that is we look at the change in potential temperature with respect to time. Now in this image here is where we do that, and you can actually see these blue dots here are actually how it changes with respect to time. And you'll notice a few points at which we see a couple jumps. And this happens to occur right here, where we see sort of a peak right here, and right here as well, where we see sort of a peak right here. So we kind of pick a value that kind of extends beyond the noise of the background. You can see how these kind of vary, but because it's never perfect. It should be well mixed within the boundary layer conceptually, but you know, the world is not perfect. So you can see how this line here, it's sort of the gray outside of this shaded area here is where we're expecting to find a transition from the boundary layer to the free atmosphere. And so you see we have kind of like 2 here, 2 here, 2 here, and then 2 down here. So we have about 8 of these, okay? So then we just take a simple mean difference of a certain amount of value, of a certain amount of points above and below these points. And here we have this for carbon monoxide. And you can see for the first 3 points on here, which is these 2 up here and this one right here, we actually see concentrations less than 0. That means our free troposphere actually had a lesser concentration in carbon monoxide than our boundary layer. But as we move forward, we begin to see large increases. For instance, particularly at our 5th point here, if you count that, that's probably, these are 4. So this one right here, we see an increase. And then even at our 8th one, which is this one right here, we see a drastic increase. So you can see how we can kind of determine how mixed is do we expect to see more mixing up here, more mixing down here based on the concentration levels? And then we kind of look at all this and we then compare it with our LiDAR imagery. So our aircraft here is actually, our C-130 is actually going in the opposite direction as our B200. So this is actually the same region. Also, the time is different because this is in UTC and this is in local time. So, but overall, you can kind of see the same features right here. You can see how we have sort of a decrease and then some peaks, and we also have a decrease and some peaks. And you can look at sort of the backscattering and see where this, you know, kind of appears to be sort of the boundary layer top around about, you know, 2,000 meters. And we're flying in our B200 at about 2,000 meters. So, you know, we can expect to see potentially some crosses. And then we can also look at how there are various, how it changes even above that in terms of the LiDAR imagery. So we can compare and contrast and see how our LiDAR imagery is actually doing with respect to the in situ measurements that were measured by Picaro. And this is kind of what Picaro looks like. You can see how we can sort of map the concentrations. This is carbon monoxide for the same date. We actually have a high And then we have some lowers here. So yeah, this is kind of how we hope to look at the methodology. And we this kind of brings us to a few questions. We hope to do this over, various complex terrains. We're going to see how this works over different peaks and places within the mountains. And then we can look at how it changes with respect to the valley. We can compare the two and see, well, are we seeing a different sort of thing from the mountains to the valleys, right? And then from there we can see how, more even specifically, how each tracer is affected specifically. Do we see the same sort of pattern from tracer to tracer, or do they sort of change? Is there different sort of mixing to expect from water vapor than, say, methane? And so that's sort of our research questions we hope to answer by doing all this. And it's important because, once again, I'll mention, we see the free troposphere as the net of all of this mixing. After all is said and done, we see a net. And this is important for understanding what are we emitting into our atmosphere, and then what is being kept by the atmosphere. And this is actually called the Keeling curve here by the Mauna Loa Observatory in Hawaii. And you can see these are actually free tropospheric measurements, and you can see it over time that we're actually increasing in CO2. And CO2 is also a trace gas. The reason we didn't do CO2 in this measurement, by the way, is due to the complexities and its sources and sinks, due to vegetation and respiration and all that jazz. So yes, you can see how we're slowly increasing. So this is, understanding how these vertical mixing processes work is essential to understanding the more looming threat of climate change. Furthermore, we can use inverse modeling to understand the sources and sinks of these various trace gases. And in order to do that, we have to better understand how they're transporting throughout our atmosphere. And over complex terrain, this is the hardest part to do for this region due to such a large, complex regional flow. And then lastly, you can also use LiDAR instrumentation, which rely on some of these mixing processes and gradient analysis of tracers. And we can use this to determine the depth of the boundary layer. And if we can better understand how our mixing processes work, then we can better understand our LiDAR instrumentation. And yeah, these are some of our models for the CO. You can see this is sort of the emissions and how we're, they rely on these mixing processes to inverse modeling so that we can better decide, well, are we putting more out than we're taking in? All right, and that is all I have for today. So thank you very much, and have a great day.